All right, let's get started. We are very happy to have Yasha Saviliev from University of Colima, Mexico, telling us about geodesic counting invariants.
Okay, well, thank you very much for the invitation. It's going to be a pleasure to give this talk. So let me just very quickly set up some basics. So XG will denote a Riemannian manifold. So pi1x will be the set of uh, free homotopy classes. Non-constant. And L beta x, the free loop space in class beta. So then we have the S1 quotient. So this is just the naive S1 quotient. So by the so S1 here is acting by reparameterization. So by reparameterization action. Um, so stop me, please, if you have any questions. And okay, so an element here I'm going to call a geodesic string. So just for brevity. Um, so then we can look at the space of class beta geodesic strings. So this is some terrible space in general. So if this is compact, we say that G is admissible. Okay, so when it is admissible, we can perturb to metric G prime so that G prime has finitely many non-degenerate um, geodesic strings in class beta.
Yes, a quick question. Does metric show up in a definition of the free loop space in class
No.
beta?
Yeah, no. Yeah, this is just regular free loop space. Um, so it's just showing up here. The
But
say
when you say this is called the geodesic strings,
Oh, these are, yeah, I guess I should say something like G geodesic strings. Oops, did I delete something? Oh no. Uh, G geodesic strings. Space of here. G geodesic strings. Yeah, so this of course, yeah, depends on on G, and of course admissible also depends on beta.
I
Uh,
see. I see. Okay.
So okay, so this depends on beta. Um, right. So non-degenerate. Uh, Basically, it's the usual Riemannian geometry non-degenerate, or from Morse theory perspective, it just means that as a critical point of the energy functional, it's maximally non-degenerate. So, right. So geodesic strings are always closed. So this is just talking about closed geodesics here. Okay. So I hope we're okay so far. So then we can define a rational number. So -1 to the Morse index of O divided by multiplicity of O, where O is G prime geodesic string in class beta. Right. So multiplicity is just a geometric multiplicity. So a simple closed loop has multiplicity 1. And then a cover of it, M cover of it has multiplicity n. And Morse index, well, it's just uh, the Morse bot index of the corresponding critical point. Okay, so the first thing we need is a theorem of Fuller, is that this is actually well defined. So it's independent of how you perturb to G prime. Well, assuming you are in a suitable perturbation neighborhood. Suitable neighborhood. Um, so right. So let me give an example. So X will be the torus, and the metric is going to look something like this. So it's not quite the usual metric, because this is shorter than that, and this is in. So this represents our class beta. So in this case, there are exactly two beta class geodesic strings, and this has Morse index 1, and this has Morse index 0. So you're going to have 1 minus 1 equals 0. Okay, not particularly exciting, but yeah. So in fact, um, this is going to make more sense via the following theorem. So theorem A. If beta is primitive, so meaning it cannot be represented by a multiply covered loop, then this is just, sorry, let me turn that off. Um, right. So this is the Euler characteristic of the this one quotient. So when this class is primitive, S1 is acting freely. So this is actually just well. So the naive quotient is quite nice, and this is the Euler characteristic, right? So this is the Euler. So in general, you can get any rational number for this invariant. I say invariant, so far as just a number, but yeah. So, but the idea it is in fact some kind of invariant. So the conjecture is that so basically motivated by this theorem A, is that um, so it depends. So when it is defined, maybe let's just say when because I mean for this to be defined, I need to first find a metric where the space of beta class geodesic strings is compact. So when defined, it depends only on beta and well, and topology of X. So we
Josh, I
can
got a
use
quick question. So in theorem A, um, do you still have these assumptions that you are in a class
uh
with
right. So here G is admissible, right? So beta admissible. Is that the question?
yeah, so the L beta
Um,
X is somehow homotopically finite space.
yes, yes. So it's some kind of yeah. Yeah, so yeah, otherwise the right hand side is in principle infinite, right? Yeah.
Okay. Uh, but also the right hand side does not depend on G.
Right. Right.
That makes it interesting. Okay.
Yeah. 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 So the right hand side is purely topological. Um well, so if you do have a G admissible metric, if you do have a metric which is admissible, then the right hand side is finite, and these two numbers are the same. So of course these are integers in this case. So this is an integer. Um,
I have another question, actually. Um, is this conjecture in the conjecture by topology of X? You mean homeomorphism type of
right.
X, homotopy type of X?
Yeah, I was going to yes, I was going to so here I mean homeomorphism type, but yeah, of course maybe that's a bit ambitious. I mean maybe you could make this more strict. I mean smooth topology also. So maybe it's only smooth topology invariant.
So
I
you
mean,
expect this to be able to distinguish homotopy equivalent non-homeomorphic manifolds, for instance?
I wouldn't go that far. But I mean, yeah, but I mean, I think it's definitely too much to hope for this to be homotopy invariant. Um, but yeah, but homeomorphism or smooth homeomorphism invariant, smooth diffeomorphism invariant is it's more likely. So all right, so let me just um, all right, so let's just summarize. So basically, so in this case, we have some uh, some quantity. So we'll just say it's infinity if so X is any manifold. So infinity if X does not admit a smooth structure and admissible G, and then F G beta otherwise. So, all right. So just to have like uh, a function to rationals from set of manifolds, extended rationals. So right. So one result is that so the conjecture holds for X a surface with genus at least one. And of course, in this case, fx beta is finite. Right. So in the rest of the talk, I would like to outline a proof of this conjecture, proof of this theorem. Sorry. So in order to do that, I'm going to introduce a stronger conjecture. And it's about geodesic sky catastrophes. So let me first introduce this notion of geodesic sky catastrophes. Suppose we have right. So okay. Well, I mean, maybe I should. Right. So right. So okay. So we had this space. So just to recall, we had the space of geodesic strings. And so in general, it's not compact. But even if it is compact, if you would like to prove invariance of this f functional, you need to establish compactness for a more general space. So GT is some variation. So here GT is so smooth family metrics. And this is basically, so right, so this is the space of pairs. Oh, the GT geodesic string in class beta. Okay, so this is kind of a cobordism that we want to understand. So of course, in principle, this is non-compact. Let me put a regular. And so in fact, non-compactness is not even the main issue. The main issue is that you may have something which is called a sky catastrophe. So this is a map to this cobordism space. With properties that, right, so okay, so on this space we have two functions to R. One is the length. So L is just the length of O with respect to GT. And the second function is just the time projection, right? So okay, so then right, so we want that image of L compose F is unbounded. Well, that's what we want. Yeah, wait, that's all we want. So sky catastrophe is basically a situation where you have something like this, where let me make more space. Okay. Okay, so here you have t-axis, here's just the l-axis. So a point here is basically just right, it's t f tau. Okay, so right, so this is just a planar picture. Um, so yeah, so there is a reason I'm drawing it as a zigzag. So in fact, you cannot have something like this. So where the length just explodes in finite time. So this is not actually possible. And the reason it's not possible is because these are critical points of the length functional. In fact, more precisely, we have the following characterization of sky catastrophes. So if F is a sky catastrophe, then T compose F has infinite length. Okay, so okay, of course, I said F is continuous, so let's just say that in this case that for lengths to be defined, let's say that F is Lipschitz continuous. I don't know how to spell that, I'm sorry. So yeah, so basically you have to zigzag. So I mean maybe the zigzags are very wild, but you have to have some kind of back and forth behavior. Basically, I mean, if you don't zigzag, you have this kind of graphical blow up, and uh, here you have unbounded L differential, right? Which is impossible because these are all of these OTs, all of these corresponding points are critical for GT energy functional, right? So you couldn't have such a picture. I mean, I'm just outlining, but yeah. So you have to have this kind of zigzag blow up if it exists, right? So yeah. So one note is that yeah, no example for F is known. Okay.
Are you restricting to surfaces or
No, this is now
okay.
right. So this discussion is general. So yeah. So here I'm just talking about any manifold, right? So here's any x. Any smooth manifold, any closed smooth manifold. So then, the stronger conjecture is that um, such so generically they don't exist. So generically. So basically, if you did have a sky catastrophe, so you perturb the family GT and it disappears. So perturb the family and it disappears. And basically the reason for that is I mean the intuition for that is basically because such a thing is very unstable. So you have like so all of these correspond to death and birth of geodesics, and they all have to coordinate, right? So this is some kind of infinite conspiracy, right? So all of the deaths and births coordinate to form a staircase like this, right? So that this looks very unstable. So that's kind of the intuition for the conjecture.
Actually, could you say the relation? I don't see in what sense this is implying the previous.
Ah, right. Well, yeah, it's not obvious, right? So basically, so this is say the conjecture too. It follows from Fuller's theory. So it implies conjecture one in the smooth analog, so the smooth topology analog, um, by Fuller's theory. So this is already kind of like around 1960s. Is uh, I mean, it's not exactly just Fuller's theory. I mean, I wrote a small paper about this some years ago, basically explaining this kind of phenomenon. Um, but essentially, if there is no sky catastrophe, then you can just uh, look at the cobordism space and then check invariants of the Fuller index, right? So basically, you don't have any blowups. So I mean, even if the space is non-compact, the cobordism space is non-compact, it's enough that you don't have this kind of things, right? So I mean, I don't care if there are like some disconnected components which are going to infinity. That doesn't really matter for the proof of invariance of the because here I have finitely many things, right? Here I have finitely many things. Here I also have finitely many things. So I just need to follow these things and uh, see where they end up here. And so long as I don't have blowups of like this, I'm okay. Does that make sense?
Um,
Right. So
what
this
does
this this
the
is the,
more?
this here is a picture of theta GT. And so this wiggly lines are a picture for theta GT beta. Right. So here, so by assumptions, I have admissible metrics. So I have some finitely many geodesics on the left, right? Geodesic strings on the left, right? And then to prove invariance, I want to see what happens to them as you change the metrics. So there is some kind of bifurcation stuff happening. Okay, maybe this picture is getting too messy, but all right. So okay, so ideally, what happens is you have
Oh,
maybe
this theta G,
something like
or
this.
sorry, this theta GT beta, blah, blah, blah. It's really one-dimensional thing between
No,
one
this
dimension.
is not. No, yeah, I mean, okay. Uh,
Is it a coordinate between finitely many
assuming
points?
some kind of regularity, it's going to be branched one manifold.
Uh-huh.
But in general, of course, it's quite a nasty space. But you can, I mean, it's the best you can hope for is some kind of branched manifold, branched one manifold, right? Because
Okay.
you cannot avoid these kind of bifurcations.
I see.
So, right, and then okay, so this is kind of best hope is you have a picture like this, right? So everything is compact, and then you can prove invariance using kind of Fuller's theory. So by the Fuller's theory is quite general. I mean, he doesn't even talk about geodesics. He talks about dynamical systems. Um, but anyway, so but the problem is if you have a blow up, and then so you have a blow up, and then basically the count of this I mean you can't prove invariance anymore, right? So like because this geodesic here blows up into the sky, and so there's no more invariance, right? So it's enough to eliminate blowups like this. So it's enough to eliminate that. So even if the whole space is still non-compact, it's enough to eliminate sky catastrophes. Okay, so I hope that makes more sense. All right, so then how much time do I have? Like
Uh,
2 minutes or
More than that, but
okay.
25. Yes.
So let's see. So what I want to say. Basically, I just want to sketch the proof of this, right? Okay, I'm locked out of my own. Let me just make sure of that I'm not missing anything. So are there any other questions? Okay. All right, so let me sketch the proof. For surfaces. Right. So okay. So one idea is that okay. So we've proven that there's no sky catastrophe, right? So in fact, so for surfaces, in fact, there's no sky catastrophes at all. So even sort of non-generically, and basically the idea is that if you have such a thing, so if you have such a blow up, so you have some element here. Okay, so let's say this is a picture now. This is a slightly different picture. This is now L beta x, and this is time. So I'm just graphing. I'm basically just graphing f. And right, so right, so basically as tau goes to infinity. So we have the length O tau go to infinity, but they're all geodesics. So only one or two things can happen. The number of self-intersections of O tau goes to infinity. And these are unsigned self-intersections. So or the multiplicity of O tau goes to infinity. So for a surface, this is the only possibility. I mean, it's some basic Riemannian geometry argument. And well, this is of course possible by topology. So this is ruled out because we're in a fixed homotopy class, right? So since beta is fixed and is not infinitely divisible, The
Yeah,
second,
here, for the case of surfaces, I mean, as a consequence, you want to prove that the um, this sum over Morse things
right, the
is the
F
same
complement.
as, yeah, the F is the same as the Euler number of the quotient of the loop space.
No, we are just proving, yeah, I mean, we're, well, you see, the Euler is not really defined anymore. So in that, so that theorem was very specific to primitive classes.
Uh-huh.
So so what we're proving is that is only that this is independent of G.
But is
So
it calculating some sort of Euler
and
number?
well, this is something that I would like to happen, but the problem is that the Euler number is not defined. Um, um,
When you say it's not defined
that's kind of
because
generality.
it's
So
not
it's a
finitely dimensional
yeah, because
object.
basically because basically this thing here. So so even if you think of it as some kind of orbifold, it's not really an orbifold. Right, so it's some. I mean, maybe at best it's some kind of orbifold CW complex. But the theory of Euler characteristic it doesn't really behave very well. Well, at least the known theory doesn't quite apply. So, well, this is something that I wanted to discuss at the end, but basically, yeah, I mean, uh, okay, basically, I don't know what is, I don't know what should be, what this should be. Um, Uh, but yeah, so far I'm just proving that it's independent of G, and then maybe if you knew how to define this, then maybe you could prove equality. But that's another it's another step.
So you take the quotient by S1 because you're interested in unparameterized loops.
Right.
Okay,
Yeah.
thank you.
Um, right. So I was saying that the only possibility is the number of self-intersections goes to infinity. And so, but you see, we have a homotopy here. I mean, we have a homotopy. So here you have something with finitely many self-intersections, and then it goes like this. And the point is this is a very regular homotopy because you're going through geodesics or things which are representable by geodesics. So uh, so we get a very regular homotopy. So tau goes to so basically no kinks and no tangencies. Right? Because geodesics cannot have kinks or tangencies. So the self-intersection of it cannot go to infinity. So we get a contradiction. Right? I mean, so I mean the only way, right? I mean, the only way you can increase the self-intersection number is by introducing a tangency, right? By deforming like this. So if there's no kinks or tangencies in our homotopy, then we cannot take the intersection number to infinity. And so and that's the contradiction. But this is of course just an outline because I'm kind of skipping some differential geometry in this step. I mean, but I think it's kind of believable. Right. So with regard to Sam's question, right? So I think, I mean, this is of course a very non-topological argument. So it would be really nice to have a topological argument, basically. So we would like, and of course, it should generalize beyond surfaces. So we'd like to define this kind of some kind of Euler characteristic. Um, right. So this is a rational number. So depending only on topology of X. Yeah, I think it's too much to hope that it will be homotopy um, invariant. Um, but I don't know actually. I mean, I don't really know very much about this kind of orbifold Euler characteristic theory. But as I understand, at the moment, this doesn't quite exist. Um, right, basically because it's some kind of singular infinite dimensional thing, right? Well, so anyway, but if one could define this, I think then one could probably prove that that you have an equality. And that would prove the conjecture in general. Yeah, so well, this is maybe. Right. Yeah, I should say that, I mean, what is also interesting is that if the conjecture fails, so if conjecture one, so if conjecture one is false, then sky catastrophes exist. So geodesic sky catastrophes exist. So this kind of and I think that's quite that'd be quite amazing. I think that would definitely surprise a lot of people in dynamical systems. Um, anyway, I don't think it's possible, but well, who knows? But um, well, so that's pretty much all I wanted to say. Um, and so maybe I should. I'm trying to get back the screen of people. I don't know how to do that. Okay.
I have a quick question. I came in late.
Yeah.
Are there any conditions on beta?
Beta is just non-constant.
Non-constant.
Yeah.
I see. Hmm.
Well, yeah.
Since you're done with your talk, let me
Okay.
virtually thank you for
Thank you.
talk first. Yes, more questions. So you mentioned Fuller's theory a few times.
Right.
Could you say a little bit more what this is about?
Right. So Fuller was defining this index for closed periodic orbits of smooth dynamical system. So right. I mean, so first you define it for an isolated periodic orbit. So this is basically what I define is like some kind of well, it's I mean, right. It's a rational number. So there's some kind of uh, the return index of an orbit, just like plus or minus one. I mean, it's like okay, and then you divide by the multiplicity. Right, and then he extends this to a compact set of orbits. Right, and that's kind of where right. So that's kind of where interesting ideas come in. So his argument is quite ingenious, like actually. So using differential forms, and yeah, it's quite hard to understand then, but now we can understand this. Well, basically what he's doing is some kind of Kuranishi, putting a Kuranishi structure on the space of orbits, and then you have like some kind of virtual Euler characteristic of this Kuranishi space, and then yeah, so
Is
yeah,
there a
so
modern treatment of his theory that I can take a
I don't
look?
know if there is a, I mean, there is a topological, there's a more topological approach to his work. There is a work of Dancer. Um, so this was yeah, so uh, yeah, so they use some kind of yeah, I mean some kind of Aquarian topology stuff to I mean there's also some other ingredients. I don't exactly remember, but anyway, they definitely avoid kind of the nitty-gritty of differential forms that Fuller does, but basically removing all the ingenuity out of it and just using some machine, some algebraic topology machine to prove invariance, local invariance of this Fuller index. Um, yeah,
I
so
see.
but I don't exactly remember the the ingredients. So um,
Great. Any other question?
Is this proof for a surface about the independence outlined in, or written down somewhere we can read?
no,
Okay.
no, this isn't just you're the first ones to hear about it. Yeah. I mean everything, but everything else is written down. So just the outline is still in the air.
All right. Well, thank you, Yasha, again
Yep. All right. Thank
for
you.
the talk. Uh, thanks for joining in the early morning.
Yeah. Yeah. Okay. Well, yeah, we'll be in touch, I guess. I'd like to
Yes,
hear more about your ideas about this BG.
yes,
Yes.
yes, we'll do. Yeah, thanks for your time.
I'll
Uh,
I'll I'll, I'll read Morita's book again to see what he's saying.
yes, yes, I'll be in touch.
Yeah. Okay. Bye
Thank
bye.
you so much.
Bye.
Bye.